Okay, so maybe we can start the talk now. I think people can join over time. So today we have Chris here, Chris Pattison from CalTech. He's working on quantum error correction, and he has been like, I mean, he has many interesting works on quantum error correction. But today he will talk about this his work on quantum fault tolerance with constant space and logarithmic time overheads. So there has been a lot of push towards reducing the space and time overhead for fault tolerance recently, and uh, and I believe this is the closest that we have so far. So yeah, I mean, looking forward to see the new techniques and tools that Chris has, and like how he managed to achieve what he has achieved. Yeah, Chris, maybe you can start. Yeah.
Yeah, so this is there's a lot of techniques here that kind of come together to prove this result, which I'll state the result later. I'm going to focus kind of on like some very high level aspects of this and kind of brush some of the more interesting proof ideas under the rug a little bit. But I'm happy to talk about that later if anybody would like. Um, so first, let me give some motivation here. In general, I want to know what a large fault-tolerant quantum computer of the far future might look like. And there's some other like fundamental questions on like what is the fundamental limit on the overhead of quantum fault tolerance. So what's the best that we can do in terms of resource usage? And then um, and additionally, whenever it comes to like say very shallow circuits and stuff like that, there may actually be some complexity theoretic implications on um, where noisy and noiseless computations start to differ quite dramatically, kind of like once you start to look at like sub-logarithmic depth complexity classes for like circuits and stuff. So for our purposes, I'm just going to assume that I want to simulate some quantum circuit of some depth that's like polynomially sized. So it's we actually don't need this assumption. We can get away with something that's like much looser, but let's keep that. And then so what we prove is the threshold theorem. And so the idea of a threshold theorem is we map, we're given some quantum circuit, and we'd like to map it to a new quantum circuit such that the output distribution of these two circuits are close in, say, like total variation distance or something like that, whenever the fault tolerant circuit is subjected to noise, which we can roughly think about as independent. We can actually go a little bit stronger than that, but let's think about that, and that the noise should be not too large. Um, so you can think of this P star value as something kind of close to a threshold. And then what we'd like to study is, okay, what's the ratio of how many qubits does my fault tolerant circuit use relative to the original one, and what's the ratio of the depth of the fault tolerant circuit again to the original one. And if anyone has questions, please feel free to I don't know, type them in the chat or something like this. Um, so let me just get the model of computation out of the way just to clear things up. So I have my width, I have my depth, and then I'm going to consider this thing that's I like to call the volume, and it's the width times the depth over this epsilon, and this is kind of the parameter that all our bounds are really in terms of. And we're going to require that that's also polynomial in the width. So there's no like pathologically super, super deep circuits or something like that. I'm going to assume that I have long range gates. So this isn't really like a geometrical logical setup or anything like that. And then I'm also going to assume that I have some noiseless classical computation that's very short depths still. But it's so I'm going to assume that I am allowed every layer of quantum gates some very short layer of classical computation. Um, and then you can think of it as that every gate fails with probability p. And then let's assume that the circuit that I want to simulate is just Clifford plus T. Equivalently, Clifford plus TCZ. Equivalently, you can use T, but for some reasons that'll appear much later. CCZ is just a lot easier to think about. So any threshold theorem has kind of a few, like kind of a general outline. Your main tool is a quantum error correcting code. And the first thing that you need to be able to do with this quantum error correcting code is you need to just be able to store a state, like keep a state alive in the presence of errors and using noisy operations. So you need to figure out how to do the logical identities. This is what we call an error correction gadget. And then once you have the error correction gadget, then you kind of have some set of easy gates. Frequently, these are Clifford gates. In our case, they'll be Clifford gates actually. And then you typically have some hard gates. So this is frequently something like T or CCZ. So you may have heard like gate teleportation, magic state injection, all these stuffs is related to techniques to get like this hard gate in the gate set, because we can't have you may have heard like sort of transversal gates, where we just apply that gate kind of component-wise to all the qubits in our correcting code block, and that applies that corresponding logical gate. And we cannot have a universal gate set that's fully transversal like that. But then once we have the universal gate set, then okay, great, we get our threshold theorem after some like counting and stuff. So you kind of build up the gadgets in this way, because frequently your hard gate gadget requires that you do some Cliffords or something like that. So you might be familiar with like, say, magic state distillation, where you're going to apply a bunch of Clifford gates in order to distill out a good T gate. So in terms of threshold theorems that are known here, so our story kind of starts off with actually so some work by Aharonov Ben-Or, some works by Kitaev, Laflamme, Zurich, and sorry, I've forgotten the last person. But kind of in the 90s, people were like, okay, fault tolerant threshold theorem is possible for any width and depth overhead. And at that point, the net best known width and depth was both polylog in the number of gates in our circuit. And sort of there's this folklore result that surface code achieves, that using a surface code, you can get also polylogarithmic depth and width. This is kind of what we expect to be using with quantum computers, soon. But more recently, it's been shown that we can actually get up all the way down to constant width overhead, so that the ratio of the number of qubits in our fault tolerant circuit and the circuit that we'd like to simulate, that's a constant ratio. So kind of along this direction, there's some subtleties about the model of classical computation, but I'm not going to get into that. Some work by Gottesman and Fauzi, Graspelli, Leverrier kind of showed that using sort of constant rate quantum LDPC codes, in this case, a variant of the hypergraph product code, could achieve constant width overhead, or that you could achieve constant width overhead fault tolerant quantum computation with polynomial depth overhead. Since then, we now know, okay, you can get all the way down to quasi. So there's a question of like, okay, what's the best we can do whenever we have like just purely constant width overhead? So very, very recently, we had this result of Yamasaki and Kawashi with these concatenated quantum Hamming codes. So it's a concatenated code construction, much like the constructions of the 90s and early 2000s, but the block length grows and the rate approaches 1 as you concatenate more and more, and that suffices to get you constant width overhead. But unfortunately, you do get this like super polylogarithmic depth overhead. So this is, you should think of this as growing faster than any power of a logarithm, but still subpolynomial. And then very recently, and essentially in parallel with our work, it's been shown that you can get all the way down to polylog using just kind of the good code families that we have today. And then our result gets all the way down to almost logarithmics. And to do this, we need to use kind of a stronger code family, not just these quantum low density parity check codes, which, sorry, I'll define in a moment, but actually something known as a quantum locally testable code, and I'll get to that. And so kind of there's this is like there's kind of this long line of work in terms of constant width overhead fault tolerance, going back since 2013, and this is kind of the best that we've gotten so far. And I personally suspect that log is probably optimal. You can tune this for the most part. You can tune this log. You can put it in the width or the depth, um, and trade these parameters off a little bit. But it seems that there seems to be some obstruction at log, which I'm not sure I will get into today.
So
Um,
basically, can I ask a question, Chris?
yeah,
Yeah.
yeah.
So like I mean, you started with assuming that, like the noise model is independent error. And so let's say if I assume, like my noise to be correlated noise model, like there is some non-Markovianity, I mean,
Mhm.
which is very much like, realistic, right? I mean, we see that in
Yeah,
systems.
absolutely.
So
Yeah.
in that case, like, does the overhead increases? I mean, like definitely the threshold will suffer, but does also, like, I mean it's are there studies, like, or do you think, like, you have some intuition on some fundamental bound similar to the log overhead that you have intuition for? I mean.
So it's really hard for our tools to really say anything, like, because this is really a quantitative question. Because yeah, we would expect some threshold, and then once you have the threshold, then all our scaling analysis applies. Um, and indeed, there are kind of various works showing very stronger threshold theorems under various models. Um, I think the tricky part is getting like a quantitative estimate here, like analytically. This is actually quite hard. So really, it's hard for me to really say. And like certainly the prefactors are going to get worse. Um,
Okay.
I think I forgot to mention this, but the prefactors in our construction are absolutely massive. So it's this kind of really like kind of an asymptotic thing, but I expect kind of you can suitably more like optimize it for the practical regime, maybe at some cost, in the asymptotic performance, and that might get you somewhere like practically relevant. Yeah. Okay, great. So and yeah, and again, I'll define these quantum LDPC codes and these quantum locally testable codes in a moment. So in terms of our gradients, this is this high level diagram that's gonna show up several times throughout the talk. And this is, so I'm essentially giving an outline. So we're first going to start with the quantum error correcting code that we use, kind of our hammer. And then we're going to construct a single shot decoder for this. So that's contribution number one. And then, so we're going to do is we're going to use transversal gates. So every CSS code has, for example, transversal C0, and we use this fact a lot. And then we have, then we're going to construct gadgets to inject, to create kind of bad logical states that we're going to use as resource states for teleportation. And then we're going to use that to construct stabilizer states, which we're going to use to teleport Clifford gates. And then we're going to use all those to do Clifford gates to construct our to do state distillation to get our magic states for CCZ, and that's going to give us our main result, roughly. So that's kind of the outline. So yeah, we start with some low fidelity resource states. We distill them with the transversal gates, and then we're going to perform the teleported gates. Great. So now let me begin with kind of some standard pieces that appear in a lot of threshold theorems so far. Well, except for the locally testable code. So if I have so QLBPC code, it's a CSS code defined by two check matrices, the X basis checks and the Z basis checks. And we say that a code is a quantum locally a low density parity check code if both these check matrices are sparse. So the number of non-zero entries in any row or column is of constant size. And that's going to give us some nice properties, which I'll elaborate on later. And we say that a code is further quantum locally testable if the size of the syndrome, so the number of violated constraints, the number of violated checks, is large relative to the size to the reduced weight of the error. So if we're very, very far from the code space, we can easily detect this because we'll see a lot of violated checks. Likewise, if we're very close, we can also easily check this because we'll see very few violated checks. And this is actually a highly non-trivial property that's only been constructed in like very, very recently, earlier last year. So the code that we're going to use is this code of Dinner, Lin, and Vidic. And these are quantum locally testable codes with almost optimal parameters. So they're a constant rate. So the number of logical qubits encoded per code block is almost as good as it could, or is as good as it could be asymptotically. And the distance and soundness is, again, almost as good as it could be. So it's so the soundness parameter here, we might hope for a constant here. We don't have this yet. These are that would be like the asymptotically optimal scaling. But we can get, so right now we know how to construct up to 1 over polylog soundness. And then the distance is not quite asymptotically good. It's again off by this like 1 over polylog. So these are almost to the best possible parameters, but not quite. And that's going to cause us some troubles later. But I'll get into that towards the end. And then we constructed what's known as a single shot decoder. And what the single shot decoder is that you process, so you measure the checks of the code. So these are the,
sorry. So
yeah.
like Chris, like it seems like this code by the
Mhm.
new like when it came, it assumes it has some underlying, I mean, like some assumption, right, about some properties of linear maps, like I mean, they had some conjecture.
Yes. So good. So this, right. So they require a certain constant sized object, which is related to a tuple of 4 linear classical linear codes. And you need that they construct or that they satisfy a property that's sort of similar to expansion. And earlier this year, there was a claim to proof of this property by CalTech and Panteleev, earlier last year. And we now very recently have had this this claim property or the proof of the property published or posted to the archive. So yeah, so everything is good there. Thanks for bringing that up. Yeah, so the conjecture is no longer required. It's result in the affirmative. Okay, so we constructed this what's known as a single shot decoder. And roughly what it is that if you have some syndrome with some measurement error on top of it, as long as that's not too large, then then your residual error after applying the correction output by the decoder is proportional to the number of measurement errors you have. So kind of this is a best you can hope for in the presence of measurement errors like we have. So this is kind of a necessary ingredient for fault tolerance because, well, our operations are going to be noisy, and we have to be able to maintain the quantum memory, right? We have to be able to perform the logical identity. And one thing I'll say about this is that this decoder is just a greedy bit flipping decoder. So as it turns out, a lot of these quantum LDPC code families based on expansion, you can just greedily flip bits, and that will, if the error is not too large, that'll allow you to find the newest code word, or like a lowest weight or a low weight correction. So okay, so Now let's perform the logical identity. We have our decoder, which we need to process the syndromes. So given, so the way you should think about this is I'm going to measure the checks in my code. Here's a measurement of the operator x, 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 x. I'm going to introduce a plus state, perform some C naughts, and then measure this in the x spaces. So we have some input error, which is going to be detected. We have some new errors that are applied in the circuit. We have some measurement and a measurement error, and then we have sort of the sum of the new error and the input error. And since our code is LVPC, what that means is that we can measure all the checks of the code in constant depth. And each check is only of constant size. Each data qubit only participates in a constant number of checks. So kind of the amount of error that's introduced is actually very well controlled. So, and actually the measurement errors as well. So roughly you can think of it as, okay, well, the Hamming weight of the measurement error is related to the block length, and the weight of the new error that we applied is also proportional to the block length times some polynomial in P. And so we'll eventually be tuning that P to be kind of small. And in particular, if this P is so it has to be less than this like our relative distance of the code, or like the guarantee that our bit flipping decoder gives. And if we can do this, then kind of our output error is also small, and it's again related to the block length, but it's a smaller constant than these words. So we're good. Great. So that's the identity. And what you can show is then, like, roughly you should think of it as that the probability of a logical error, if I just keep applying this gadget, is exponentially small in the block length of the code, actually in the distance. And so what that's going to motivate is we're going to take our blocks, our QLDPC code blocks. We're going to have a lot of QLDPC code blocks, and each one's going to be very, very small, like the log of the number of gates, actually a little bit bigger because of this polylog factor that appears here. But let's not worry about that. Really, you should focus on the log, because we're going to have these like polylog log factors appear like all over the place. So, okay, so I showed you how to perform the logical identity, right? You have your greedy decoder, you measure the syndrome. I believe somebody has a question. Maybe.
Yeah, Andy, I think you have some question. Maybe you could unmute yourself and ask.
Oh, hi. Sorry, I was typing in the chat.
Yes.
Hi, Chris. So, why is logical error of this form? Like, how does it come from this output physical error?
Yeah. Okay. Great. So essentially, what it is that so we have this guarantee that okay. So in particular, so our decoder has this requirement on the input error that essentially, if the input error is small, or rather, sorry, the input error plus the syndrome error is small, then the output error, like the residual error, will also be small. And so kind of what small means is kind of there's this like kind of this ordering of constants that you need to ensure. But you should roughly think of it as what's the probability that if I have like some bit string of length n, and it comes up 1 with probability p, on average, I'm going to have n times p ones. And the one and it coming up 1 is, you should think of that as it being an error. So what's the probability that the Hamming weight is some like extreme value, right? So this is coming out of kind of a tail bound. And so that's how you get a logical error rate of this form is this is the probability that I have like that I just happen to have like a lot of errors in that single time step on my code block.
Okay, thanks. Yeah.
Great.
But Wouldn't this depend on the decoder as well?
That's right. Yes, yes. It's absolutely a decoder dependent statement. So this is under our decoder, our bit flipping decoder. It's a statement that's dependent on the decoder, the syndrome extraction circuit. So really what you should think of whenever I say error correction gadget is that's something that is dependent on especially code, decoder, and syndrome extraction circuit. Absolutely. Yeah, you should think that's like one atomic unit.
Okay, thanks.
Great. So, okay, so now we know how to fix errors. Now let's talk about how to do computation. What you should think of now as, so these codes, they encode more than one logical qubit per code block. And that's going to cause some challenges. So first off, you should think of as, okay, these qubits are packaged up into what I call a register. And then we're going to perform transversal gates between registers. So what that means is that kind of each logical qubit, label them like 1 to k. And you just perform this operation component-wise. So if you have a CSS code, then performing a C0 component-wise on the code block performs a C0 component-wise on the logical qubits. And same thing with measurements. We have to decode, but let's not worry about that. We also get arbitrary poly qubit or arbitrary poly operations for free. So you can apply any pattern of logical poly operators. So these are kind of the initial easy gates. Well, okay, these are very easy gates, and we're kind of going to bootstrap ourselves up. And then we're going to leave them with the error correction gadget from earlier. So if we do this layer of gates, we're going to introduce some errors. So we have to suppress them by applying the error correction gadget. So that's these are our very easy gates. Okay, great. So another piece that we need is sort of this gate teleportation, which goes back to, I think, the 90s. And the general idea is that if I apply a teleportation circuit on the Bell state, where I've applied a unitary to one half of the Bell state, then I can conjugate the fix-up operations in order to have the final output of the teleportation circuit be that state with the unitary applied. And this fix-up here, if U is in some level of the Clifford's hierarchy, then the fix-up is in the next lower level down. So in particular, okay, if we have if this U is a Clifford gate, then this fix-up, this is a poly fix-up, these two. And all these operations I can apply on registers using my component-wise measurement in C0. So I only need, as long as I have this resource state, which is the stabilizer state, I only need transversal C0 and measurement and arbitrary polys in order to actually consume the state and apply a teleported gate. So now,
Chris, this is a very high level question. So obviously, I mean, so you want to bypass the Easton theorem, and that's why you have to do all this gate teleportation and so on. But then there are so many approaches out there. Let's say, suppose you take two quantum locally testable codes, and you might want to do code switching between them. Basically, my question is I mean, let's say this is our approach. I mean, and just one approach, right? I mean, what if I go by another route? I mean, does it help, or you think that in all different ways, you the cost will be same? I mean, overall.
So you'll definitely get better constants by okay, as for magic states, for applying like third level gates, I really can't say there one way or another which one's going to have better constants. But for this is really kind of the nice part about gate teleportation is you need to know so little about the code, right? It's a very black box way of doing things. So this is kind of you should think of it, I guess, more as a proof technique. And for any practical purposes, you would like that the majority of your gates are okay. Maybe you have some easy Clifford gates, maybe you have some hard Clifford gates to do, but kind of yeah, for practical purposes, you should really be using kind of more properties of your code to use to so that like your gates are very, very simple and you don't have to prepare these resource states at all. Yeah. So this is kind of a proof technique to make things as simple as possible. Uh, Otherwise, it just
Yeah,
gets quite
I mean,
involved.
maybe you will tell later, like, which step, like, is the most resource costly. Like, I mean, like, though it's log, but still, like, I mean, and why do you think it's
Mhm.
so tight that, one can't go beyond log? I mean,
Well, there's, I think, a
yeah.
question of asymptotic tightness versus like actual constants.
Yeah.
I think our
No.
constants are very, very important.
I mean, yeah, obviously, I mean, asymptotic tightness. Yeah. Like, I mean,
Oh,
yeah.
asymptotic tightness. Yeah, I'll get to that.
Yeah.
I think, yeah,
Yeah.
that's, yeah, there's kind of the two different regimes in which you'd like to optimize for. So, um, um, yeah, so since we're distilling uh, our stabilizer states, one of the things that we did was that we're distilling them in bulk. So instead of distilling, you run some costly distillation circuit and you just get one stabilizer state out or one resource state out. We're actually going to get many, and that's going to kind of allow us to amortize the cost, much like regular error correction. Um, and so what we're going to do is we actually want very few distinct states to distill, very few types. Um, and then this creates this question of, well, okay, we have these component-wise operations. How do we entangle the different coordinates, right? So we have, so one operation that we have to add into the gate set is this kind of this operation that takes the qubits and applies kind of a rotation to the register. So it maybe sends, in this case, I've drawn a rotation by 2, and we actually do by powers of 2. So so the first two states that we're going to resource states, the first two gates that we're going to distill resource states for is one is we're going to just swap the first two logical qubits in our block in between two blocks. And then the other resource state we're going to use is we're just going to apply this rotation of the block by, and we're going to have one for every power of 2. And for convenience, let's just assume that the number of qubits is also a power of 2. It doesn't change much. And then we're going to get the standard stuff. We're going to apply CZ to the first two coordinates, Hadamard, S, measure the first two coordinates in either the X or the Z basis, and then also this a CCZ to the first three coordinates, and that's going to be our third level gate, is CCZ. So this is our full gate set that we're going to distill resource states for. So we're going to use the transversal gates to consume our resource, to prepare and consume the resource states, and then there's going to be a resource state for every logical operation. So you can already see that this is probably not optimal in terms of constants, but it's probably asymptotically pretty close to optimal, up to like sub or up to like log factors, polylog logarithmic factors. So, okay, so now I have to tell you how I'm going to get these resource states. So the nice part is that whenever I do the whenever I teleport a one of these like stabilizer states, it's a poly fix up, which is nice. I can do this with transversal gates. And so we're going to do this multi-level distillation based on these like quantum Hamming codes. And so this is kind of the easy analog of magic state distillation. It's the same premise. What you're going to do is you're going to start with a product state of noisy product state of the resource state that you'd like to distill. Then you're going to project this into the code space, and then you're going to do error correction and then unencode from the code space. And the fortunate part is that we can use some of these techniques from Yamasaki and Kawashi to get constant rate. So constant ratio of input to output states with like arbitrarily small output error rate. And this procedure of like doing repeated rounds of distillation has a lot of similarities to code concatenation, which is kind of that's where that comes in. And then because we're concatenating, we also use this trick to reduce the depth, the overall depth of our distillation circuit. Kind of, you do one round of distillation, you unencode from that, you do another round of distillation, unencode, which is why we're able to avoid picking up like this quasi polylog-log factor that you see in the Yamasaki-Kawase results. And then for reasons that will be apparent later, we're not going to have any insulas. So you start with the products. So you start with a bunch of registers, initialize to the state that you want to distill. You perform the distillation circuit, and then you have kind of a less noisy version of your state that you'd like to distill. And then, logically, we start with some input error rate that's below some constant, and then we have some output error rate that's doubly exponentially small, and the number of levels of distillation that we've run. So kind of as you would expect from distillation. Now I need to tell you how to get these like noisy input states. So this is actually kind of a bit of a hack, and really this is somewhere where I think that there's actually a lot of room for improvements in the non-asymptotic setting. Asymptotically, again, this is probably pretty tight, unfortunately. So the construction is that we start with we can just write down a constant depth encoding circuit for our quantum LDPC code that uses, constant quantum depth encoding circuit for a QLDPC code. It's not fault tolerant or anything like that. And so that circuit can be, to prepare the resource state, we can say, okay, I'm just going to encode I'm going to prepare the resource state like unencoded, and then encode it into my circuit, into my code block. Okay, that has a super constant number of gates, so the failure rate of this thing is going to go to 1. No surprise here. But then what we're going to do is we're going to run the encoded version of this circuit, this state prep circuit. So we're going to take the circuit and run it in a concatenated code, a very small concatenated code, as such that so we can kind of simulate this non-fault tolerant state preparation, and this entire procedure is going to fail with some rate that's constant. So with maybe say probability, I don't know, 1/3, we fail. With probability 2/3, we successfully prepare the resource state that we want. In reality, I think the constants need to be a lot stronger than that, but you can get the idea. So kind of we can succeed in preparing this noisy resource state. There's this actually so now there's this tricky bit of what happens whenever this circuit fails, right? A encoding circuit, whenever it doesn't really have any locality constraints. You can imagine that if I mess up a single bit there, or a single gate, that error is gonna propagate to like very nearly the full code block, right? And that's no good, because then our state is very, very damaged. And then it can actually be so damaged that we can't do further error correction on it. So there's actually worse states than a logical error. So recall that our decoder required that our error is not so large, right? So if it's large, then this is something analogous to a leakage error that you may be aware of on the physical level, where so not only can you not fix it, but every time you touch it, like if you have this kind of like logical leakage and then another block and you do a gate between them, it's going to leak both. And so it's just going to spread through the computation, and then all of a sudden none of your error correction gadgets work. So we need to ensure that these don't escape into the rest of the computation when we prepare them. So we have to very quickly identify, okay, this code block is close to the code space, this code block is maybe not, let's toss it out. And so we need to verify that our error is small with these noisy measurements. But this is exactly what a quantum locally testable code does. Recall that that we can detect if you're close or far to the code space just by counting the number of ones in the syndrome. And so roughly you can think of it like this. Sorry, that's leaked over onto the next page. So roughly you can think of the syndrome for quantum LDPC, or for quantum locally testable code, as this behavior where as the error gets larger, so here I've plotted the reduced error weight, and here I've plotted the syndrome weight. As the error gets larger in a generic QLDPC code, it can't be too large because of essentially like, because there's only there's an upper bound on the number of stabilizer generators that touch the error. And in a generic QLDPC code, there are very high weight errors with very small syndrome. So you're not really going to be able to detect the difference between this case and this case. Whereas with the QLTC, kind of the Hamming weight lives in this cone. So if we're very far from the code space, we'll see it right away. And then so what we can do is that we prepare these noisy input resource states that potentially are so damaged that we cannot do computation on it. Then we're going to measure our stabilizer generators. And if we see too high of a syndrome, we're just going to toss it out and prepare another one. Actually, we prepare many in parallel and only take the good ones, but it's the same thing. And so, okay, we're going to have some false negatives and false positives, but we have good control over that, and that'll be okay. Sort of the probability of a false negative. So false negatives are very bad because then our entire computation can fail. Kind of we can bound the probability of having a false negative in terms of the size of the measurement error. Okay. So that's kind of all the ingredients that you need for preparing stabilizer states, which is kind of the easy gate in our scheme. Is everybody happy with that so far? So now let me kind of, I know it's getting a little bit late, so let me briefly go over the magic state part of the scheme. So here, so we're going to do distillation again. But here we need a code with a transversal non-Clifford gate. And really the only way I know how to do this is by like algebraic constructions. So think like Reed-Solomon codes, Reed-Muller codes, these sorts of things. And for those of you that might be familiar with Reed-Solomon codes or kind of these algebraic constructions, it's just storing the evaluations of some low degree polynomial with coefficients in a finite field. And if we have larger finite fields, that means we can consider polynomials of larger and larger degree. And what we showed is that there for an extension field of F2, or for larger and larger extension fields of F2, there exist codes, punctured quantum Reed-Solomon codes with essentially constant rate and linear distance and a strongly transversal CCC with the multiplication in this extension field. And don't worry about the technical bits of that statement. Just know that this is the necessary ingredient that we need to do state distillation, except now we're working with qdits of size 2 to the n, for n somewhat large. Roughly the strategy is that we're going to take, just like in the Yamasaki-Kawashi case, where we took growing quantum Hamming codes, we're going to take growing quantum Reed-Solomon codes with the qdit size growing as well. And then we're going to simulate these things, because we only have qubits, we're going to simulate these qubits using qubits, and we can do this without too much trouble. And we can simulate all the necessary qubit operations that we need in order to do the distillation. At the end, we have sort of this CCZ state for the qubit, and then we're going to convert it back into a binary CCZ state. And so, and if we do that, we can get very good error suppression. So in particular, the error suppression is, it goes roughly, you can think of it as it goes like exponential to the product of the distances that of each step in the distillation. And so if you have growing codes with growing distance, you can get slightly faster error suppression than doubly exponential. And this kind of relates to kind of this long open conjecture about the asymptotically achievable rate for magic state distillation. So you may be aware of this conjecture or this work of Hastings and Hoff from 2018, where the rate of input states to output states, magic states to output magic states, was like polylogarithm in 1/epsilon with this power. So since then, we've had some recent constructions of code families that allow you to get much better than polylog, either sub polylogarithmic, or even just no dependence on the error rate at all. So there's some recent work using algebraic geometry codes. This will be a plenary talk at QIP. Our construction is quite a bit simpler than that. We're just concatenating kind of the simplest codes you can imagine. And then we also get sort of sub polylogarithmic dependence on the output error rate of the distillation scheme. So kind of this is a simpler way to accomplish it. And in fact, because the concatenated structure, this gives us the lower time overhead compared to just maybe distilling at once with like a very large algebraic geometry code or something like that. So even if you were to use some of these AG codes, you would still have to do some of this concatenation with known constructions so far. Let's see here. So, okay, so you're essentially going to do the same thing. There's some complication with the Clifford fix-up, so we can't actually distill kind of coordinate-wise our states. We only can do like one magic state per block. So this introduces some serialization cost. But overall, it's going to be the same as in the stabilizer state distillation. So we are going to start with the constant input error rate, and then our output error rate is actually going to grow e to the minus factorially of the number of levels, because we have a slightly growing block length, and that gets us the this is actually the source of our little o of 1 in the in our time overhead. Okay, so now let me just assemble all these ingredients. So okay, the actual construction is quite involved. We take this QLTC of DLV, we construct a single shot decoder for it, and then we can use this to grab error correction gadgets. We use transversal gates, it's very straightforward. Then we use the QLTC property and the concatenated code scheme of Aharonov-Ben-Or to create state injection gadgets. We use these two pieces to get the stabilizer states. Then we use our construction of the punctured quantum Reed-Solomon codes to get the efficient distillation scheme. That gets us our CCZ. And that gets us a fault tolerance scheme with a slightly vanishing threshold. And I'll get to that in a moment. So roughly you can count up, okay, what's the cost we've paid so far? So we have to do this serialization procedure where we do only one logical gate on one for each block. Each block can only participate in one teleportation gadget at a time. So this incurs a serialization cost. And so this is actually the source of our log here. And it seems very hard to fight this. You can trade space for time, but ultimately it seems like at the very least you're going to have to serialize or encode less than a constant fraction number of logical qubits per block. So we have some time.
Sorry, can you repeat again? Like from where was this log coming? This the gate serial.
Yeah. So recall that our the way we do all our gates is gate teleportation, and I only know how to do gate teleportation between blocks, like say 2 blocks, right? I only know how to teleport one gate between those at once, or on that pair. So you can imagine the worst case circuit, which is just pairwise, say, I don't know, controlled S or something like this, right? Followed by like random Hadamards or something. Then the number of gates, the number of blocks that you have to touch to do all the gates corresponding to a single block is proportional to the number of logical qubits in that block. So if you can only if in a single time step you can only do gates between pairs of blocks at a time, then it's going to take you at a time on average the number of logical qubits in that block.
Yeah.
And our blocks are roughly log sized. So this is the cost. This is our main cost. We also have self-leading factors. So some log coming from that we have some number of multiple gates that we have to do in a serialized fashion. So we do like maybe all the CCZ gates, all the Hadamard gates, all and so on and so forth. We have some polylog logs coming from the stabilizer state prep, and then actually the magic state prep. This is actually the source of our little o plus 1. It's actually this ratio of the or rather it's related to this gamma factor that I showed earlier. It's not quite that, because it actually counts the ratio of gates that you have to do instead of ratio of input states to the number of output logical states. But you do incur serialization here. So ideally you would like to get to remove this log so you can truly get down to log times polylog log factors, but that's we're not there yet. And then okay, so we had a slightly vanishing threshold. So okay, what we can do is we can actually simulate our scheme. So we can concatenate with the Yamasaki-Kawashi constant space overhead fault tolerance scheme, just to reduce the input, the error rate that our scheme sees just by a little bit. So what that means is that kind of everything slows down by the time overhead of the Yamasaki-Kawashi scheme. The time overhead is related to the amount of error suppression that you demand for the scheme. And in our case, it's quasi-polylog log of the number of gates in the circuit that we'd like to simulate. So just to conclude, our main result is we can take this polynomial size quantum circuit. It doesn't have to be polynomial size, but let's keep it with that. And we're going to construct a new circuit that runs in slightly greater depth that fault tolerantly simulates the original circuit under roughly local noise. And the amount of classical computation that we're going to do is slightly super constant. And that's just for convenience. This can be removed. There's actually a lot of things that we do here that don't appear in earlier fault tolerance theorems. So this is the first threshold theorem, to my knowledge, that uses that incorporates distillation in an end-to-end proof. We also had to introduce a new analysis for a new method of analyzing fault tolerant circuits, that associates kind of these families of these bad fault sets that cause uncorrectable failures with polynomials. We we also introduced this new magic state distillation scheme that also achieves kind of this gamma going to zero, which is a simple refutation of this Brahe-Hastings conjecture from 2014. We have a simpler gate addressing solution, which I expect to be relevant for practical schemes. And this is actually the first time that we needed a quantum locally testable code. So I didn't really touch on this, but that if we did not have the quantum locally testable code, we'd have to measure the syndrome many times in order to be certain about our syndrome outcomes, and that would incur another factor of log. So we actually used a locally testable code in a non-trivial way for fault tolerance, which is actually kind of unusual. This has never been done before. And so there's kind of some open questions. I guess the first one is, okay, is this log depth optimal? I think it is, because of this example of like a random circuit with 2-qubit gates. And does there exist a constant rate magic state distillation code with a short depth encoding circuit? So this is needed in order to not incur a large time overhead and just do the magic state distillation all in one shot, like in one round, as opposed to having to do this concatenated type scheme that we did that incurred this little O of 1. Thank you. Thank you.
Nice. Okay, thanks, Chris. So yeah, I mean, this was a very nice talk, and I think, yeah, if people have any question, maybe please unmute yourself and ask.
Hi, Chris. I have a question. Thank you for the very nice talk. I've always wanted to read this paper, but it's a bit involved.
It's very involved. It was also very involved to write.
Yeah. So yeah, I have one question. So would you? Okay, I understand you have all these individual pieces, sketches, but would you outline like how you piece them together? I guess it might has to do with the new fault tolerant analysis you talked about.
Yes.
Yeah.
So kind of.
I mean, yeah, I've read the concatenation threshold and also the constant overhead threshold proofs, and like what you like what's your techniques?
Yeah.
How you did differently.
So you may be aware. I'm not sure if you've ever read the Aharonov-Van-Or threshold theorem proof. But there they kind of their main tool is to say, okay, if so faults exist in space-time locations in the circuit, which you can think of as, okay, I have some operations, they're faulty. And as long as the fault is sufficiently sparse, the output of the circuit is correct. And what sparse means here, in what they showed, is that it didn't that there weren't too many faults in particular, like rectangles, space-time rectangles. What we do is that we say that actually the fault should not contain any of what we call bad fault sets. Kind of what this does is it allows to separate out what those fault sets actually are with kind of the combinatorics of working with them. And then we associate these family of bad fault sets with polynomials, kind of very similar to a weight enumerator from coding theory, although it's kind of it's not as nice, I would say. Then what this allows you to do is, so first off, this means that we're working kind of in a more adversarial setting, but our techniques are suitable for stochastic noise. Adversarial noise is really, really nice because the statements are much cleaner. Whereas in the stochastic noise setting, your statements are horrible. It depends on your distribution of noise and such like this. But this allows us to kind of only introduce the stochastic noise in the very last step, actually. More or less, you can think about it as if we have a circuit, and so in working with these polynomials, we can, if we have two gadgets and we want we went to upper bound the probability that they both fail simultaneously. It actually turns out that we can just we can assign bad fault paths, bad fault sets to this setting, and the weighted numerator of that corresponds to the multiplication of the weighted numerators of the bad fault paths for the two gadgets. So kind of you get something like independence of errors, which you actually don't get in a stochastic noise model. And then if you want to do like an upper bound, what's the probability that my fault contains this bad fault path, or like any of these bad fault paths? It actually turns out in the local stochastic noise model to correspond to just the evaluation of the weighted numerator at the parameter of your local stochastic noise. So that allows us to get kind of independence working in this setting with correlated noise, and allows us to track everything a lot nicer. Of course, we have union bounds that corresponds to the sum of the polynomials. And then concatenation corresponds actually to evaluating the polynomial, the evaluation of another polynomial, roughly speaking. So we even can get concatenation working as well. And so roughly that's how.
Okay.
So everything goes together by kind of assigning these weight enumerators to all the to all the gadgets, and then showing that, okay, if the fault set restricted the gadget doesn't contain any of these bad fault paths, then the output of the gadget is good. That roughly the output error is correctable.
Okay, thank you. Yeah, I think I get the high level idea. Yeah.
There will be in perhaps about 2 months, there may be kind of a simpler sort of formalism paper discussing these sorts of things. So if you're interested in particularly those proof techniques, as opposed to the actual sort of fault tolerance construction, you might want to hold off on reading this paper.
Sure, thanks. And another quick question. So at the start, I remember like to have all the things hold, you assumed existence of this quantum LTC code. And were you saying like the latest paper by Pentelev, they proved this thing exists?
Right. So in particular, we directly did. So our work depends on the QLTC of Dennard-Lin-Vidic, and the QLTC of DLV requires the construction of these small-sized local codes, which we were aware of a proof of this construction of Pavlichev and Pantelev, and that proof has recently been posted on the archive as of 2 weeks ago.
Okay, thanks.
So there's no our result is unconditional now.
Okay.
Yeah.
Thanks.
Hi. Thanks for the talk. And I have a questions like regarding a note you put in this picture. So say the photon scheme has like log V vanishing threshold. What does that mean? Like, does it mean it has vanishing threshold like compared to the constant threshold in general?
So okay, so in the final threshold theorem, we want a threshold value that's independent of the circuit size. So because we right, so for convenience, we worked with our decoder only corrects against adversarial errors. So we need that the weight of the error is less than 1 over polylog, a certain 1 over polylog of the block size, which is and the block size is itself logarithmic in the number of gates. So we require that our error rate P is like 1 over log of the number of gates. That's not good enough for a threshold theorem. So then we have to do this small simulation with Yamasaki and Kawashi, some small amount of concatenation in order to boost our threshold up to its constant value.
I see. Thanks.
Yeah.
Yeah. Okay, I think we are already past 11. So in this case, like I think I would thanks Chris again, and yeah, like thanks everyone for joining. Uh, See you guys next week. Yeah, thanks, Chris. Yeah.
Thanks for listening.
Yes, I've stopped it. Okay. Okay.